So, I will be your guide on today's AST trip. And our trip will contain a few points that I want to mention for you to understand what AST is and how it works. So this is a map. This map will guide us through our trip. Every place that will appear on this map is a vital point that we need to explore to reach our destination. But before we start, I need to tell you a bit about myself and why did I decide to go on this trip at all. I love to learn new stuff. As a programmer, it means ideas, concepts, and especially for me, languages. And that's why I call myself a polyglot, because I don't like to get attached to one language. There's too much that each and every one of those can offer me to just stick to one. Because of that, I also don't like to get attached to IDEs. I hate them. I mean, before you start using a new language that you want to learn that has so many different concepts, you first need to learn a complex IDE to do anything. You need to have a specific editor to compile a project, which is like total crap. And that's why I love JavaScript, because it was born as a language that will run everywhere. You basically you can program in JavaScript using Notepad and run the script directly in your browser. Here on the screen, I have a React app that's, as previously mentioned in the first presentation, is live reloading the code without any hassle in Vim, using Vim as the IDE for that, which IntelliJ can't afford for stuff like Java or other languages. But there comes a point when you need to increase your efficiency, some tooling that all the biggest languages have, and JavaScript for some reason doesn't. For example, I want to rename my variable to something else without having to install a complex IDE. I want to create a method automatically, reformat something, get auto suggestions. And currently, previously at least, my Vim editor, my Atom, my Visual Studio Code, Emacs, whatever, besides two major players, Visual Studio and IntelliJ, couldn't give me that. And the truth is, I did not know that I did not know till a few months ago, why is it that? I was struggling in my beloved Vim, looking with a bit of jealousy at the Java guys in my company, whose most pressed key is enter, because the IDE does everything for them. They just need to press enter to program, which is nice. And in reality, as Uncle Bob said in one of his blog posts, that for some reason, the tooling for the new languages doesn't evolve as fast and isn't implemented as fast as it needs to be to keep it consistent when it goes to productivity. So how do we keep the productivity of that the tooling like IntelliJ and Visual Studio give us in C# or in Java, while writing in a language that is newer, that doesn't have so many aspects in it? And until one day, I didn't know that. But one day, I've stumbled upon a thing called flow type. And the interesting thing about it wasn't the type safety or the 100% increased coolness factor that I have as a developer because I'm using the newest technology. It was the fact that, thanks to that, my Vim received superpowers. And the superpowers was auto-suggestion. I could get auto-suggest without changing anything in my code. I didn't have to create an IDE project. I didn't have to change my folder structure, add RAM to my computer so that the IntelliJ would somehow work there. I just got something for free. So I thought to myself, once we got autocomplete, how hard will it be to get more functionalities, like refactor, like extracting a method, like extracting a variable? And this is where the urge to start the trip of where the AST comes from. I wanted to be able to add functionalities to my editor without all the bloat that other editors have. So let's go on our trip. The first stop is called Parsing. And here, let me just enlarge this, if it works correctly. Perfect. Here on the left, your left, we have a sample code wrote in JavaScript, ECMAScript 6. And on the right side, we have an AST that it's parsed into. So a wise thing to do now is to say what an AST is. So thankfully, the code on the left tells us that. AST stands for Abstract Syntax Tree, which is a tree representation of source code, essentially what programs see other programs, how our browser reads our code. They do not contain a lot of information about code like white space, and once built, other information are added to it. The AST is built from elements, and the main element types are statements. For example, like this variable declaration here. Expressions, like the object expression here. Identifiers, like the ID of this key. Literals, like string literals, and blocks, like the whole program itself. So as you can see, the whole AST is a tree representation of our code. So let's go further. What can we use that knowledge for? We can use it, for example, to read what is under our cursor. So because we know that in this certain place we had a string, and in this certain place we had an object expression, we can get additional information about it. Or can we? The thing about JavaScript, as like everything else in the world, is that context matters. It's not that simple. And there are a lot of edge cases where something under your cursor isn't exactly what you thought it was. And it's because the code is pretty dynamic in JavaScript. But we can get closer to what we think is there by getting a bit more knowledge from the AST and going through it in a very specific way. And this step is going to be called Traversal. This is the way we walk through the AST to decide on what should be on what place. And why is it so important? Because JavaScript is constructed in a way that we need to do it in a specific way to get consistent results. And the main thing about it is the scope. And here talking about scope, JavaScript's working on a lexical, JavaScript has lexical scoping working in it. It means that scope is represented also in a tree structure where blocks, each of those blocks, create a new scope. So here we have a global variable, a variable 1 declared in this scope 1, and a variable 2 declared in scope 2. Code within a deeper scope may use a reference from the upper scope, and the lower scope might also create a reference of the same name without modifying it. So if we checked it wrong, what is at what place, we might be getting different results depending on how do we walk around the tree. So we need to be very wary of the scope. We need to make sure we don't break existing code while modifying different parts of it. We may want to add references to variables. We may want to remove them, change references, and many other stuff we need to achieve our refactoring functionality we want to do. So there is a specific way to do that, to keep it safe. And we are going to achieve that using the visitor pattern. And here's how it works. So here on the top, you have a code sample that I'm using here. On the bottom, you have a visitor, an object that's containing keys which represent callbacks which should be launched when you arrive at a very specific path. The path will be displayed here, and the console output from this console log will be showed there. It will get simpler as I go through it. So when we start our traversal, we start at the function declaration at the top. Our path is function declaration, and because this isn't an identifier, we don't have anything in our console. When we go to the first identifier, so we recursively go deeper into the tree, the path changes, and the path is now the function declaration ID. We get the console output, and we go further. Now we get n as the first parameter of our function, and we can go further and further and further, always going from top to bottom recursively, with when arriving at the last node, we exit. So we move back to function declaration, and if there was another place we could go lower, we will go there. And here I have an example of how this would work in our AST Explorer. So if nothing screws up, oh, it did. Maybe I'll try here. Give me a second. Yes. OK. So besides those timeouts, I'm not going to filter them now. So anyway, if someone sees it, maybe I'll try to enlarge it. Perfect. So here it's the same code. We get visiting square first. Here is the code snippet we were working on. Here is the visitor that's being launched every time we go a next step in the traversal. And here is the AST. We'll leave this step for now, for later. So, whoa, for some reason my presentation went like nuts. Give me a second, sorry. I hope nothing breaks besides that. Oh my God, spoiler alert. It shouldn't be that way, okay? I think I'm here, yeah. Okay, so what we got, we wanted to achieve something like on the left. We need to find expressions that are under current cursor. We need to find occurrences of found expression. We need to find the expression scope, and then we can add a variable declaration to the scope and replace picked occurrences. So I'll just turn off this console. Yes. Just as on the left, we want to extract thing that is under our cursor into a new expression. So how do we achieve that? We already know how to find expressions. We just need to go through the tree, find an expression, see if it's exactly the expression we're looking for, deciding on where its position is at, and then we have the position as the result. Here, for example, we put the start position at 0 and at 1, which means that we're selecting the first 5. Then we can find all the occurrences by picking the 5 we just found and getting its scope traversing through it and finding all the other expressions that are equal to this one, which we will get the result of array of expressions with the same type. And then we got the first 3 steps that we needed to extract the variables in our code. So the 4th and 5th step needed to do that will require transforming the tree. Here on the top left, we got our example of the AST, and in the bottom left, we have an example of a visitor that is changing the node name. And changing it to its reversed version. So here, for example, we had an identifier named AST. We've changed it to TSA, and so on in every identifier occurrence. Oh, not like this. So using a transformation like that, we can, for example, add something to our scope. In our, in our case, we want to add a reference to a variable. We want to add a variable declaration. So how do we do that? We just go to the path, scope, generate a UID identifier for a variable. So it means that we create a variable name that doesn't exist yet in the scope, and we push it to our scope. Thanks to that, after this transformation, our code from 5+5 changes into reference declaration and 5+5. We can also replace our identifier that we are currently selecting with the identifier name, and combining that, we can get a declaration at the top and change the number literal into the object itself. So we've made it. We are able now to pick to find an expression. We are able to replace it with a definition, with a new extracted. But there's one more thing that we didn't talk about yet, and that's the generating of the code back from the AST. So there is one problem with our previous stuff that doesn't take into account one very, very necessary thing we need to take care in our application. Anyone sees a problem with this code? I mean the input and the output, even though we didn't do any transformations. Yeah, the colon here. The colon here is very important because it means that, as previously mentioned, AST doesn't contain very much stuff that is needed for us to generate our code back. We don't keep the information about white space. We don't keep the information about punctuation marks. We just store it as a tree without many, as you can see, even highlighted, without many of the necessary information that's required to bring it back to the previous state. So how do we achieve that? We don't use an AST. We use something called CST, which stands for concrete syntax tree, which besides having all the nodes required for generating the code back and traversing through the tree, we also have tokens, which this code consists of. Here in this example, the blue points are the nodes, same for AST and CST. The red lines are the paths, as mentioned previously, and the blue texts are tokens. So thanks to that, after taking that into account and changing and generating the code only for the stuff we've changed previously, we can assure that if we traverse through a code and generate it from an existing AST, we get the same stuff as the output, yeah. So the last thing to do is the demo. So pray to the demo gods. I will go here. You may see it's not Vim. Yes, it's not. For this demonstration, I'm going to be using Atom. And this is how the code works currently. The package that I've been working on works currently. So I'll put the mic down for a second. So for example, if we had our previous 5 + 5, and we wanted to extract it, we just press Ctrl-C, Ctrl-Alt-C, or Command-Alt-C. We pick the expression that we are interested about, just like in IntelliJ or something like that. We find all the interesting occurrences for us in this scope, and we replace it. Then we rename it to new name. This is what many companies are selling for a lot of money that can be achieved in few lines of code if you know what you're doing. Here, the same example, when extracting rather than only one expression, the whole binary expression rather than only the 5 addition. Here, for example, something that the other editors don't have yet, extracting into the new syntax from JavaScript in the destructuring syntax. Also, you might notice that when I try to extract another stuff from the same code, we get it connected together here. And also working for this methods. Of course, working for both consts and lets. Yep. So going back, I have like a minute left, so I'll just talk about one more thing here. It's interesting how to test this stuff, at least for me. So how do you test that something went through your program and it went out correctly? I've created a small parser and code builder that takes files like this, where I define the input to editor input, so code input. I provide the positions of the cursor that are here, and I provide the output that should be after the extraction of the code. And it's working like that. This one? Yes. Okay. So, without further ado, we went from parsing through traversal into transforming to generation of the new code. These are the materials to study. Bubble plugin handbook. You can check flow types GitHub, AST Explorer, and the package that I'm working on currently is called FactorX. And thank you.